Greetings for all. My name is Jônatas Santos, and I'm presenting the paper entitled Improved Model for Vocal Folds with a Polyp with Potential Application. This paper were presented together with Jugurta Montalvão and Israel Santos, and we are from Federal University of Sergipe. To give a brief overview on the presentation, in this paper we proposed a new mathematical model for vocal folds with a polyp. With this model, we generated some samples and employed them to perform some analytical conjectures about polyps and what happens in the presence and in the absence of polyps. So we could see that intrinsic dimension and differential entropy might be some relevant features to discriminate it. So we performed a naive classifier as a proof of concept to verify it. We verify this relation. And with this work, we aim to provide a complementary tool to help speech therapists or other specialists to analyze and identify characteristics of vocal polyp on voice. So to begin, what are vocal polyps? In this figure, we could see that this red dot is the vocal polyp, but what are they? They are some kind of lesions, and these lesions are generally caused by trauma. Uh, this trauma is related to abuse, misuse, or overuse of voice. And in the presence of a polyp in the vocal folds, it creates an irregular vibratory pattern. So one of the folds vibrates irregularly, so it creates a rug effect on the voice. So the voice would sings rug, would sounds rug. And also the polyp creates an incomplete closure of the vocal folds. So the folds gets more opened when it should be closed, and it creates a leak of air. So with this leak of air, uh, this voice produced sounds breathy. So the voice of vocal polyps, let's say like that, are rug and breath. And in this paper, we use a mathematical model for vocal folds. And these models generally are based on mu-elastic aerodynamic theory of phonation. And they, as we could see as with these examples, they use generally lumped elements. So it means that they use damper, mass, and Springer. And here we have two examples that are examples of interest because we created our model based on these two models. First, on the left side, we have story and pizza model. That is a body cover structure model. So it respects the body cover structure of vocal folds. And it uses a layer of masses to represent the cover of the vocal folds and uses another layer of one mass to represent the body. And in this model, they use a trachea and a vocal tract to represent the complete production of voice. And in the model from Zhang and Zhang, we could see that uh, we have a less complex model. It's a simplified model, and it uses an extra mass to represent the polyp. But it don't uses an vocal tract and trachea because the focus of the paper in which they use it was on the dynamics of the vocal folds, and then they don't use it. But we wanted, and we want to join this model together, create a model based on both of this. And to analyze the samples we will synthesize, we could use the intrinsic dimension and differential entropy. The intrinsic dimension is related to the free variables of the data we have, and the differential entropy is related to the effective hypervolume this data occupies. So we could see here two sets of data as example, in which this data were in higher dimension, in 3 dimension, and we could see that this data is actually in an inner structure that is in a lower dimension. So in the case of the left figure, we could see there is a two-dimensional inner structure, and in the right we have a one-dimension inner structure. So we could see that this is the intrinsic dimension, this inner structure in which the data were placed, and is related to the number of free variables that generated this data. And the differential entropy is related to the effective hypervolume. So it's related to the hypervolume it occupies on space. And with these measures, we could uh, project data into lower dimension and high entropy spaces, because it are some things that might improve the performance of tasks like regression, classification, clustering, and data visualization. So let's remember again. I said that these two models from Story and Thesis and Zhang and Zhang were specific of specific interest for us because we wanted to join them, and this is our model based on both of this. So this model we proposed uses the body cover structure and adds an extra mass to represent the polyp. And here we have the motion equations, in which we have equation for forces from the spring, for the damper, for the connection between masses, and also for the aerodynamic forces acting on the masses, on the folds. And to calculate this the variables related to the model, we could use the areas between masses of both sides. So to calculate the area between the polyp and the other mass on the other side, we use the displacement of the polyp mass added to the displacement of the other mass, and all of this multiplied by the length of the polyp mass. And to calculate the other areas between the masses of both sides of folds, even the lower or the upper mass, we use the length of the glottis multiplied by the sum of the displacement of both masses of both sides. And for the glottal aerodynamics of this uh, model, we use this a simplification of the equations from theta, and we use two sets of equations. One for the open glass condition, where we have a jet flow and a Bernoulli flow, and another set of equations for the closed glottis condition. So here have the pressures based on the subglottal pressure, on the supraglottal pressure, and the hydrostatic pressure. The hydrostatic pressure is the mean of subglottal and supraglottal pressure. With these pressures, we could calculate the aerodynamic forces acting on folds. So here we have these forces that are calculated by the product of the length of the glottis and the thickness of the area of the mass in which the force is being calculated, and the pressure acting on them. To calculate the glottal flow, it was used the Theta's equation and was added a turbulent flow based on the Reynolds number. And for the vocal tract, we discretized the area of the tract and also the area from the trachea, and used these discrete measures based on the data freely provided by the open source software Letalker 1.22. So here we have representations for vowel A and vowel I, the vocal tracts, and in both the trachea is presented in the orange lines. And for the synthesized sinus, we also use the vowel U. So Then we need to set the parameters of the model. And to this, we use some rules that were used to relate muscular activities to model parameters. So we have uh, some parameters for the activation of the cricothyroid muscle, for activation of the thyroarytenoid muscle, and the lateral cricoarytenoid muscle. So with these measures, which vary in this range presented here, we could calculate the values for the stiffness, the mass, the damping, the thickness, the adduction, and the glottis length. And also, we will need the stiffness for the polyp that is fixed at 140 kilograms per second square. And some others, the damping factor from the polyp is calculated uh, based on this value. So with this, we synthesized some normal and pathological voices, and we got more than 800 samples. And for who is interested in this, the samples are available at our website. So with the synthesized samples, we made some conjectures, and we could see that simulated polyps induced random amplitude fluctuation. As we can see in this figure, after the onset of voice, the vowels with polyp present a relevant fluctuation, and this is not observed in synthetic vowels without polyp. And uh, this fluctuation and this observation made us wonder, is entropy and local intrinsic dimension good measures for polyp detection? To verify it and continue the conjectures, we made some 2D projection of phase space trajectories. We know that in the phase space, perfectly periodic signals appears as a one-dimensional closed loop, while the random noise tends to deform this trajectory. So we got this with the samples we analyzed. And we could see that for synthetic vowel without polyp, the trajectories seems less detached from each other and to be locally 1D. And for the other side, the synthetic vowels with polyp has these trajectories less well defined and looks to be in a higher local dimension. So we could see more clearly that might have a relation between signal entropy and local intrinsic dimension for as a important uh, tool for polyp detection. So with this, we should estimate intrinsic dimension and differential entropy. So we made an adaptation of the method proposed in Montalvão, in which we use a vector of patterns, each pattern with 6 samples of the signal, and we used 2,500 patterns as presented in this equation. And the signals were sampled with 44,100 samples per second. Uh, then to make this estimation, we use the hypercube with a hypercube with edge length r and a coincidence rates CR. So to illustrate this, we could see here in a three-dimensional space in which this hypercube is a cube, and we could see that we use this cube to count how many points of this data gets in this cube and how it varies with the change of the edge length. So the amount of data points inside this cube or hypercube is the coincidence rates. So it's a counting of this data inside this hypercube. So using this, we could estimate intrinsic dimension and differential entropy as presented here using the log of the edge length r and the log of the coincidence rate C of r. So we performed this estimation and we could see that we have a significant difference in the analysis scale of 2 to the minus 3. Here, we could see that vocal folds with Polyp produced voices that seems to be in a higher dimension, more specifically here in a three-dimensional space, while the trajectories from the voices without Polyp seems to be in a lower dimension, more specifically one-dimensional. So this points out that our conjectures might be correct, might be in the right way. So we, as a proof of concept, we implemented a naive classifier, and here to classify human voices with polyp and without polyp. So we get this data from the Saarbruecken Voice Database, which is available online, and we use it only the sustained vowel A, and we used an analysis scale of R equals to 2 to the minus 3, as we could see a difference with the synthesized model. And from the sinus, we get the samples beginning from the 3000 sample to cut the onset of the sinus. And with the classification, we got this. We estimate the threshold for differential entropy and a threshold for local intrinsic dimension. And with these thresholds, we made this estimation. The threshold for differential entropy was 1, and the threshold for local intrinsic dimension was between 1.7 and 1.8. So we get that only 22% of speech with polyps were missed, and only 23% of normal speech were classified as anomalous. So these are good results. These results are far from chance. And we could see with this that intrinsic dimension and differential entropy might be really potential features to detect vocal polyps. Of course, there is needed some further development, but we could see that this model present might be employed to fine-tuning actual polyp detectors. And one way of doing this is the data augmentation through the entrainment of some classifiers. Thank you all for watching. We would like to thank CAPES and CNPq for supporting our work, and we are very grateful for your attention. Thank you.